10 for the waiting line models. Basically, the gist of this question is that we are looking at a movie theater complex and trying to solve for different questions along the lines of, how long does it take to wait in line? How long is the entire process? How many people would be there at a certain point? The main things we just need to know right now are these two numbers here. So over an hour, they can maintain up to 280 patrons, and then like a normal active day, they would average around 210 patrons per hour. And that is exponential, so it's going to be all normal. Basically, to show you. So really, this table 3, we're just going to use only this and those two numbers we found. So the lambda, the upside down y, is going to be the mean number of arrivals per time period, which is 210, and then fancy U epsilon is going to be 280 per hour. And basically we're just going to, you can see through all these equations, those are the only two numbers that we're going to need. So let's jump right into A. So find the average number of moviegoers waiting in line to purchase a ticket. I'll go to this quick. I'll show you the formula. So average number of moviegoers waiting in line. That's going to be this right here. Average number of units waiting in the queue. Basically just another way of saying that. And so this formula, I'm going to show you where it's at right here. So it's just going to be denoted by LQ. And then that's the same formula. So just plug in these two numbers. 210 squared over 280 times 280 minus 210. That's the two numbers you're going to get. And then that comes out to 2.25 people are waiting in line. So for A, there'd be about 2.25 moviegoers waiting in line to purchase a ticket. And next up, we got B. So what percentage of time is the cashier busy? That's going to be this right here, utilization factor for the system, another way of saying that. And obviously, pretty simple formula here. It's just going to be lambda over epsilon. So let's go here. Okay, so just that 210 over 280, 0.75 or 75%. Pretty simple, just 75% of an hour is 45 minutes out of the hour that clerk is going to be busy selling tickets. Next question, what is the average time that a customer spends in the system? So that's going to be this formula, average time a unit spends in the system, pretty much the same. Obviously just 1 over epsilon minus lambda. That's going to be right here. So the epsilon versus lambda, 280 minus 210, that's going to give us 70. So 1 over 70, 0.0143 rounds out to about that. And then I just did times 60 to put it into seconds. So that's going to come out to 52 seconds. So the average customer throughout the waiting time and the time they are at the desk getting their tickets, it's going to be around 52 seconds. And then the next part of this is just a continuation of that. So just a portion of that, what is the average time spent waiting in line to get to the ticket window? So obviously we know it should be less than 52 seconds. And the formula we're going to use for that is right here. Average time a unit spends waiting in the queue. And it's going to be very similar to the formula we did for A. But we can just use this since we already figured out the average number of units waiting in the queue. So that's going to come out to right here, 2.25 over 210. That's going to come out to 0.011. It's going to round to that, and then just do the same thing we just did for that. So times 60 times 60, and we are going to get 39 seconds. I mean, that seems about right. We know that it's less than that. And yeah. Okay, so for E, what is the probability that there are more than 2 people in the system, more than 3 people, more than 4? So this is probably, I mean, it's not very complicated, but somewhat of the most complicated part. It's just this formula, so it's really not complicated at all. Let me show you. This is their example. So basically, they have it just a table that you plug it into, and then it's going to keep going down because the chances that there's more and more people there are going to be less than if there was like 1 or 2 people there. Let's go here. So I just made this kind of table. It asks for 2, 3, 4, but really you could plug in any number. So 210 over 280, that's going to simplify down to 3/4. I mean, we did that right here. 0.75 or 75%. So just put in that 0.75, and then you can just plug in these numbers. 2 plus 1 obviously is going to be 3, so it's going to be 0.75 cubed, and then that's going to come out to 0.422 or 42.2%. All these are just percentages. And like I said, it's going to keep going down. So the chances for there to be 3 or more is going to be 31.6%, and the chances for there to be 4 is going to be 23.7%. That's just plugging in these numbers. And yeah, that is all the answers.